I'm going to try a little bit to channel some Bill Kennedy energy here, but no, it might be impossible, but I'm going to try. All right, so let's get going. So I think the introductions are already done, except for the part that I work at the New York Times. So I actually, before COVID times, I used to bump into Angelica in the hallway all the time. So what we're going to go over today, I'm just going to give you an overview of the project we're going to be working with to do the comparison, and then we're going to talk about, we're going to go through what the project looks like in Arduino, what it looks like in MicroPython, CircuitPython, and then TinyGo. And if we have time at the end, I'm going to go into a more detailed example to kind of show some really cool features of TinyGo, like being able to use Go routines for things that are kind of gnarly in Arduino. Okay, just a little, I'm going to stand on my soapbox for a second here, just before we get going. I hear this all the time, like I build cloud solutions. Why should I care about microcontrollers? Well, one of the things is that, to invoke Bill Kennedy again, his concept of mechanical sympathies. I think working with microcontrollers, because you have to work within a very constrained environment, and you have to understand exactly how the machine works in order to get the best out of it, it really makes you a better developer. So, and also it's been known to, just being able to manifest something physical like that from your code, it gets the creative juices really going. So, and that kind of spread out to your entire life. So, microcontrollers, yeah. All right. What are we going to be doing? Well, seeing as we're all at home with COVID, and you every now and then you want a high five or a fist bump, and there's nobody around. So this is what we're going to do. I hope you guys saw that video. It's a silly little machine. It turns out to be quite simple. What we have here is an Adafruit Trinket M0, which is a 32-bit microcontroller running at 48 megahertz, has about 32K of RAM to deal with. It comes with CircuitPython already installed. It doesn't support MicroPython, but it comes with CircuitPython already installed. I'll get into what CircuitPython is a little bit later. But in addition to that, we have a micro servo motor, essentially, which is going to be moving our arm up and down. And we have right over here on the right, you see these two little circles are the this emitter and receiver for an ultrasonic motion sensor. And then, as you can see in my build over here, I put it together in a little case with a battery and everything, so I can get my high five going. All right. So this is the circuit that we're going to be putting together. Basically, it's, like I said, the Adafruit Trinket M0 and the ultrasonic sensor. So very, very simple little project. Oh yeah, one thing I missed. In testing this, I did in order to do with MicroPython, I implemented this also on the WeMOS D1 Mini, which is an ESP8266 device. And I also ran this on an Arduino Nano IoT. Okay, so let's take a look at what this looks like with Arduino. So the code is pretty straightforward. You have, what you have here is you set up some we import the libraries for the servo and the ultrasonic sensor. We set up some defines for things like what pins we're going to use for the trigger pin, the echo pin of the ultrasonic sensor, the positions of the hand in terms of degrees for the servo, and our reference to the built-in LED. We instantiate our devices, and Arduino code comes with is structured with two very important functions. One is a setup function, which runs only once when the device boots up. So you put things in there to initialize components or initialize variables and set things up. And the second part is the loop function, which the Arduino environment just calls over and over again. So it'll basically run the code, get to the bottom, and do it again, and over and over and over again. So what's going to happen in that loop is that we're going to basically read the ultrasonic sensor to see how far away something is from the top. So if you look at the video here, if I put my finger, let me turn it back on again. If I put my hand a little bit above it, it slaps me. So that distance I defined as 40 centimeters, right? So if something is within 40 centimeters of the device, it will turn the LED on, wait for half a second, put the hand up. It tried to slap me over there. It's very angry. It'll put the hand up and then gently bring it back down again. Otherwise, you'll have some. Yeah, I just want to make it a little bit more gentle going back down. And that's it. Turns the LED off and waits 50 microseconds, 50 milliseconds before it does it all again. All right, so that's what the code would look like in Arduino. Now, Arduino is a really cool environment because it was created by a bunch of engineering students in Italy to make things easier and cheaper for engineering students to be able to build these prototypes and so on. It spread really rapidly and provides a really open environment for tinkerers and hobbyists as well as professionals. Okay, let's take a look at what this would look like with MicroPython. Exact same situation. So MicroPython was created by Damien George, who's a theoretical physicist. And his focus really is to make this a rock-solid environment for industrial applications like robots and control systems and stuff. I believe some part of the Mars rover, the latest Mars rover, actually runs with Python or MicroPython. Okay, so how is this structured? Just like the C equivalent, we import some libraries and some modules. We set up some constants, and then we define a function called run. This is not necessary, but it's one of the optimizations that we do with Python, because anything that runs in the global space in Python runs a lot slower than things that are run in a local scope. So for instance, if I am referencing variables that are local to a function, that's a very direct lookup to access that variable. Whereas if the variable is defined in the global space of the program, it has to go first look in the local scope, then go look up that variable in a dictionary and so on in the global scope. So it adds some extra time. So run everything in a function, and that's a little optimization for MicroPython. So the first part of the code here, basically, as I put the comment on here just to show the how it equates to the Arduino environment. So the first part equates to what you would normally put into like a setup routine in setup function in Arduino. It's one-time configuration setup code. Then since there's no loop function in MicroPython, and then the way it runs, you basically have to create a infinite loop essentially. So it's, while true is an infinite loop, and in that loop, you do whatever the action is that you want to your project to do. So in this case, just like the Arduino one, it reads the sensor and checks to see whether the sensors within your sensor has detected something within the threshold. If so, turns the LED on, moves the hand up, and brings it back down. So as you can see, let's go back to the Arduino one. So we have 41 lines of code for Arduino, 34 lines of code for MicroPython. So far, Python, true to its nature, is really concise and small. What does it look like with CircuitPython, right? So CircuitPython was actually created by Adafruit and as a fork of MicroPython because they wanted to kind of change the way it operates and how it interacts with the user, because their focus is more beginners and education, right? So they wanted to make it so that you don't have to flash CircuitPython onto a board. Your board comes with it already installed. You don't have to figure out how to connect through some sort of serial mechanism to copy up code from your machine to the board, because CircuitPython devices expose the code as a USB drive essentially. So you just basically drag and drop or edit code directly on the board, which is pretty cool. But one thing that you'll notice right away is that the approach that Adafruit decided to take with CircuitPython makes it a little bit more wordy. So you end up with longer code and more code to do the same thing. So for instance, with CircuitPython, I can set up my LED or whatever device I'm using with one line of code. LED equals pin, what pin I want to use, and to direct the type of interaction with that pin. So that pin is an output pin in this case. With CircuitPython, you must first declare your LED pin, LED device, and then set the direction with a separate call. So it's a little more wordy, but I guess for teaching purposes, it's more clear as to what's happening inside of the device. All right. So now this brings us to TinyGo. I hope that you can actually see that code there. I'm actually going to jump into an editor to show the code and some examples later, but I just wanted to show the code on here for the comparison. So, like Tobias went through, TinyGo is what it is. It's really tiny. I mean, in terms of what it produces, it's really cool. It uses LLVM as on the back end to do all that compilation and optimization of the code to generate those tiny binaries. And I think the coolest thing is that it's just standard Go, right? So aside from libraries that are specifically created to interact with hardware devices and so on, the language is just Go, which is really cool. So you get access to probably most of the standard library, the things that make sense. Like you don't need some of the more complicated parts of the standard library on a tiny microcontroller device, right? So those things may not be pertinent, but you still have access to that standard library. You get the readability of Go, you get the concurrency features of Go. And ever since it was officially supported by Google at the beginning of 2020, it's been moving really fast. So as an example, when I first started looking at TinyGo and this particular type of project, I tried, I found an example of how to use pulse width modulation, but it was only for the Arduino Uno. That code didn't work on any other microcontroller because of various reasons. And I was kind of upset about that, but then what I didn't realize at the time was that in the background, the TinyGo community was actually making changes to how all this stuff works and simplifying it and trying to make it more common across microcontrollers. So what you see here in this code is the majority of the result of that work. I think that they still have some work that they're completing, but so it's still in flux, but the results are pretty good. So what we see here is we set up our variables. We have we set up our pulse width modulation pin, actually the internal timer that's being used with the pulse width modulation. We set up the pins that we're going to use for our ultrasonic sensor and LED and so on, and servo. Actually, we don't need to set up the servo here, it's down below. And we set up our positions for the hand and so on. Down here, we instantiate our sensor on line 27. We configure it. We make sure that the LED is configured as an output pin. And just for comparison, to configure a pin for output, let's say, in TinyGo, it's the pin variable that configure machine that pin config mode, pin config pin output. Right? So it's a little wordy compared to MicroPython, which is really succinct. And in Arduino, it's basically just saying pin mode, LED, and whether you want to input or output. But it gets the job done. And I see the method to the madness, I think, because when you have more complicated pin configurations, you can put it all together in that structure, and it becomes more readable and understandable. Okay, so after all the setup portion, which runs once, just like MicroPython or CircuitPython, you need to set up your infinite loop. So in Go, this is the empty for clause. So basically, this is just going over and over again. And what it's simply doing is, again, reading the ultrasonic sensor. If there's an object within range, it turns on the LED, raises the hand, brings it back down, turns off the LED. So yeah, that's what the languages look like. So okay, let's go over this again. So we start with the task scheduler library that we import, and again that basically sets up a method of doing asynchronous or concurrent calls in Arduino. So we set up our two functions one for reading the sensor and displaying the data, and one for listening to the button. And the button press signals to switch the display between Fahrenheit and Celsius. Here we set up the two functions to be called by the task engine. One every 500 milliseconds, the other every 50 milliseconds. And here we see the actual code to read the sensor and display, blah, blah, blah. Nice thing about the Arduino libraries is that we have lots of fonts fonts available to use with the displays. And TinyGo actually has this also, which is pretty cool. I'm not actually going to go through all this code, but basically, okay, so here's the button handler that just listens for a button press. If it was pressed, it does some debounce, and it switches a flag, the show Celsius flag. And based on that, the display routine would display either Celsius or Fahrenheit depending on the state of that flag. All right, so this is the Arduino code. How would this look like in Python? Well, very similar. I mean, you have routine, you have modules for the OLED display, you have modules for the DMA 280 sensor. This is the code that deals with fonts. The issue I've had with doing this in Python is that all this code, so the fonts, just like with Arduino or TinyGo, the fonts are basically code files with bitmaps of the fonts, right? So whatever fonts you want to use with Python would have to be on the device. So if your device has a limited amount of storage space, you kind of limited in what you can actually deploy to that device. So in this case here, I'm stuck with one font. With MicroPython, the garbage collector is kind of optional, so you can kick it off by calling gc.collect. Here I set up my devices, display. Nothing really impressive here except that it's just a longer piece of code, right? Let's go to the Go version of this. You have, just like Arduino and MicroPython, you have drivers for the devices you want to use. And just like Tobias said in the previous talk, there are a lot of devices already supported, but more are being put on there as things progress and TinyGo matures. TinyFont, I'm really impressed with it. It's really cool. I think this was created by Ron, if I'm not mistaken. But I'm going to be, because of this, I think I'm going to switch to using TinyGo for a lot of stuff that I was using displays with. It's really cool. Okay, so we set up standard stuff we've seen before. We set things up in our variables. Okay, here's an interesting way I structured this code here. So just to mimic what Arduino does, I created a setup function and a loop function, and in our main, I just simply call one after the other. And setup does the setupy things, but at the end, I kick off my Go routine to listen to for button presses. And then the loop function, just simply all it's doing is reading temperature, display, read the temperature, display, read the temperature, display. And whether it displays Celsius or Fahrenheit would depend on the flag set by the button handler. So as you see here in the button handler, what we're doing is if the button is pressed, which in this case here is just, you figure that out by calling get on the button, and I just set the LED to high here just to indicate to the user something's happening, and I flip the flag and debounce by just waiting for. I don't allow the user to make another selection within 500 milliseconds or half a second. Okay, and then down here you have the code for actually working the displays, putting text on there, formatting things, and so on. And at the end, it just calls display.display to actually correct the content to the OLED display. So that is what I wanted to show there. Let me go back to my presentation. Where am I? Yeah. Okay, so just to wrap it up, I have the sample code that that shows there's 3 projects in there. Just a basic blank in both in Arduino, MicroPython, CircuitPython, and Go, so we can look at what they look like, how the code is structured in all 3. Same thing for the High 5 project, and then the last project with the BME2A temperature and humidity sensor and the OLED display. So if you go to this this repository, you will see that code. Also, I put some references on here from the Arduino website, MicroPython, TinyGo, and I highly recommend Tobias's book. I went through it cover to cover and learned a hell of a lot. Excellent book. And with that, I thank you.